Okay, here's an example about the work-kinetic energy theorem, or rather an example which uses that theorem to solve a problem. So the question reads as follows. Three forces are applied to a box. Here's our green box here of 0.5 kilograms that moves leftwards by 3 meters over a frictionless floor. The force's magnitudes are 5 newtons, that's this F1 here, 9 newtons, that's this F2 here, and F3 is 3 newtons. That's this force in this direction. And importantly for this diagram, this theta here is 60 degrees or pi over 3 radians. After the displacement, what's the net work done by the three forces? And the second part is if the box's initial speed is 2 meters per second, what's its final speed? So we're going to solve this using the work energy theorem and the definition of work in order to solve this first part. So let's calculate the work done. So for the first part, did I call it number one? It did. So for the first part, the work done, we need to use the definition of work, which is the dot product of the force with the displacement. So we know what the displacement is. It tells us in the question it moves 3 meters leftwards. Okay, so 3 meters leftwards, if we're going to just use a sort of standard x and y set of axes here, leftwards means we're moving in the negative x direction. So our displacement in I and j vector notation is going to be minus 3i. Okay, so that's the displacement. The three forces then, we can write down F1 in vector notation. Well, F1 is moving in that negative I direction, and it's of magnitude 5. So we can write down that F1 is minus 5I. F2, well, F2 is the one with the angle here, so this is a bit trickier, but it's going to have a magnitude of 9 cosine 60 degrees acting in the positive I direction. So it's 9 cosine 60 I. And in the y direction, it's going to be 9 sine theta acting in the y direction. So that's going to be plus 9 sine 60 in the j direction. And then F3, this one's nice and simple. It's acting straight downwards here. So this is in the minus y direction. So this is going to be in I and j notation, it's going to be minus 3j. Okay, so we now have everything we need to write down the work done. So the net work done is going to be the dot product of these of the net force with our displacement. So we'll have minus 5 I dot minus 3I. That's our first force. Plus, for this F2 then, we'll have 9 cosine 60I plus 9 sine 60J dotted with minus 3I. And for our F3 then, we'll have minus 3J dotted with minus 3I. Okay, so immediately we can just use the definitions of the dot product and what we know about unit vectors to point out that this term, okay, which is in the j direction, when we try to take the dot product with this I vector here, well, j and I are at right angles to each other, so this component does no work. And similarly here, we're taking the dot product between a j and an I here, this force does no work at all. So both of these components in our network are 0. And so what we're left with is the dot product between minus 5i and minus 3i. Well, I dot I is just 1. So we just end up here with minus 5 times minus 3, which is 15. Should have done that in blue. So we have 15 joules of work done here. And then from this one, well, cosine 60 is a half. So we get 4.5 I dot minus 3i. So again, I dot I is just 1. So we're going to get minus 3 times 4.5. So that's minus 13.5. All right. And this gives us then a total work of 1.5 joules. Okay, so bear in mind that the work done here is positive. That means that it's accelerating or imparting energy to our box. If we'd ended up with a negative work, then we would have found that, in fact, we were decelerating the box. Okay, so that's the first part. We find the work done by the three forces. Part 2 then, we're asked to find the final speed of the box. Okay, so to do that, we're going to use the Work-Kinetic Energy theorem, which says that the change in the kinetic energy is equal to the work done. So we just calculated what the work done is. We've got this 1.5 joules is the work done. And the change in the kinetic energy, well, that's going to be a half mv squared minus a half mv naught squared, where v naught here is our initial speed. So we're told that the initial speed is 2 meters per second. So, and we know that the mass is 0.5. Okay, so we can substitute in the mass there. So this just becomes 1/4. So that's a half times, or 0.5, just to double check. Yep, I think the mass is 0.5 kilograms. So a half times a half gives us 1/4 v squared minus a half times a half, which is 1/4 times v naught squared. Well, v naught was 2 meters per second. So this gives us then times 4. Okay, and this is equal to 1.5. We can cancel those 4s there then, and we just get 1 here. So we get v squared over 4. We'll add 1 to both sides is equal to 2.5. So v squared is equal to 10. And then that tells us then that the final speed is root 10, which is roughly 3.2 meters per second. Now, we could have solved this problem using Newton's laws. Okay, we could calculate all of the forces. We could calculate the acceleration of the box and so on. Interestingly, we're not told in what direction this initial velocity is. So we would have to be a bit careful. And in fact, I haven't done it, but I'm not actually sure that you would be able to calculate whether or not this thing had accelerated or decelerated based on knowing the initial speed. But we now know that the final speed is 3.2 meters per second. And because we know that the work done is positive, what that means is we are imparting energy to the system, so we're definitely speeding up. Okay, so this is an acceleration that's causing this new speed that we've got. But this is the way that we use the work energy theorem to solve these kinds of problems without actually having to worry about the Suvat equations and Newton's equations. This gets us there straight away.